Jai Hind students, continuing with the previous lecture, in this particular session also will continue with some selected numericals, right? These numericals are based on the universal law of gravitation as well as the acceleration due to gravity, right? So without wasting any time, let's start with the first question. First question is, calculate the value of small g, acceleration due to gravity, on a planet whose density is 1/4 that of the Earth and whose radius is 1/3 that of the Earth's radius. Now student, look, in this particular question, the planet's density is given in terms of the density of the Earth. So first and foremost, we need to recall the expression for acceleration due to gravity in terms of the density of the planet. We know that the value of acceleration due to gravity, it is given by g capital M divided by r square. This is the mass of the planet, this is the radius of the planet. And in case we consider rho to be the density of the planet, then mass, you are aware, it's volume multiplied by density. So if the planet is considered to be sphere, its volume would be 4/3 pi r cube. So substituting all the values, what we get is 4/3 pi r rho g. This is the formula for the acceleration due to gravity in terms of density of the planet. Rho is the density of the planet under consideration. Clear, students? So in this question, this is the formula to be applied, right? Okay. Now let's check the value. Calculate the value of g on a planet whose density is 1/4 that of Earth and whose radius is 1/3 that of Earth's radius. Suppose, put this as equation number 1. This is the value of acceleration to gravity on the Earth's surface. This is the density of the Earth, this is the radius of the Earth. Now, for planet, suppose the value of acceleration due to gravity is g dash. It will be equal to 4/3 pi r dash. R dash would be the radius of the planet. Rho dash would be the density of the planet. Rest 4/3 pi capital G, they are constant, isn't it? Now, as per the question, it is given that the density is 1/4 that of the Earth. 1/4 means 1/4. And radius is 1/3 that of the Earth's radius. So what you get is 4/3 pi, radius is 1/3. So r dash is r/3. Rho dash is 1/4 of the Earth's radius, Earth's density. So rho dash is rho/4. So it can be rearranged in this particular manner. 4, 3, 12. You can write 4/3 pi r rho g. And this, from equation 1, it's the value of acceleration due to gravity on the Earth's surface. So g dash is equal to 1/12 of g. So students, this is the result. The value of acceleration due to gravity on a planet whose density is 1/4 that of the Earth and his radius is 1/3 of the Earth's radius is 1/12 the value of acceleration due to gravity on the Earth's surface, right? You can get the numerical value as well. G is 9.8 on the Earth's surface divided by 12. So that will give you the answer in meter per second square. Clear, students? You can express the result in terms of small g as well, right? G is the value of acceleration due to gravity on the Earth's surface. So we are done with question number 1. Students, let's proceed to the next question. We are supposed to find out the height above the Earth's surface at which the value of acceleration due to gravity reduces to half its value on the Earth's surface. And we are supposed to express the result in terms of capital R. Capital R is the radius of the Earth, right? So question number 2. In the theoretical section we have discussed, students, the value of acceleration due to gravity decreases with the increase in the height, right? It decreases with the increase in the height. So we're making use of that appropriate concept. So suppose this is the Earth's surface, right? So this is the center. Its distance from the center would be r, which is the radius. So the value of acceleration to gravity at a point on the Earth's surface would be gm divided by r square. Suppose this is point B at a height h above the Earth's surface. So at point P, the value of gravity is suppose g dash. So it will be given by gm divided by, what's the distance of point B from the center of the earth? It is r plus h, isn't it? This we have done in the article. So it is r plus h whole square. So if you divide these two, second divided by first, what we get is g dash divided by g, it will be equal to r square divided by r plus h whole square. Right, students? Now, we are supposed to calculate the height above the earth's surface at which the value of small g reduced to half its value on the earth's surface. So it's given. It is given that here the value of acceleration due to gravity is half the value of acceleration due to gravity at point A, which is a point on the earth's surface. So g dash is half g. So g dash by g would be equal to half. So r over r plus h whole square, isn't it? Now what to do is, taking square root on both the sides, what we get is r over r plus h, it will be equal to 1 by root 2. So after this, what I've done is taking square root on both the sides. Now if we solve it, what we get is root 2r would be equal to r plus h, or h would be equal to root 2 minus 1 into r. Root 2 value, it's 1.414 minus 1 into r. So students, the height of the observation point above the earth's surface at which the value of acceleration due to gravity reduces to half its value on the earth's surface is 0.414 of radius of the earth. So this is the answer. Or this height is 41.4% of the earth's radius. So at this point, the value of acceleration due to gravity will reduce to half. Right? So we are over with question number 2 as well. Question number 3, students. It's a very, very important question, and this is the question which we'll try to do considering the theoretical aspects. Whatever we have discussed theoretically, we have discussed the variation of small g on various factors. The value of small g decreases with the increase in the height, isn't it? The value of small g decreases with the increase in the depth as well. And at a point on the earth's surface, the value of small g is found to be maximum. So we need to depict all those mathematically derived situations graphically. So, third question. This is suppose the distance from the center of the earth. It can be considered to be smaller. This is the center of the earth. O is the center of the earth. And this is the value of acceleration due to gravity. Right, students? So consider this case. This is earth. This is the center of the earth. Right? This is any point on the earth's surface whose distance from the center would be capital R. Yesterday we have discussed at a point D, which is at a depth x below the earth's surface, the value of acceleration due to gravity at point B is g dash is equal to g1 minus x by r. That is g r minus, this is the formula which we have obtained theoretically, isn't it? This is, student, the value of acceleration due to gravity at point B, which is at a depth x below the earth's surface. G is the value of acceleration to gravity at point A, that is on the earth's surface, right? With the increase in the depth, the value of small g decreases. And we have discussed, at the center of the earth, the value of acceleration due to gravity is 0. This we have mathematically verified, right? So, this distance is r minus x. This distance from the center of the earth, it may be considered to be y. So, g dash is equal to g by r into y. So what I mean to say is that if this y is 0, then g dash will be equal to 0. That is, at the center of the earth, the value of acceleration due to gravity is 0. And with the increase in the value of y, the value of g dash will also increase linearly this is constant, G by R is constant. So with the increase in the value of Y, the value of G dash will also increase. With the decrease in the value of Y, the value of G dash will also decrease. And eventually when Y is 0, G dash is also 0. Isn't it? So this is the distance from the center of the earth. It can be considered to be smaller as well. It can be considered to be smaller as well. So basically, if this is the radius of the earth, this is the center of the earth and this is the radius of the earth. So as we keep moving away from the center towards the surface, the value of acceleration due to gravity increases linearly. And at a point on the surface, the value of acceleration due to gravity is maximum. So linearly means we will get a straight line, right? So here its value is Gm divided by R square. At a point on the surface, it is small g is Gm divided by R square. Thereafter, students, if the height is increased, then we are aware small g is given by Gm by R square, isn't it? So in that case, it will vary like this. So this is the Earth's surface and this is beyond the Earth's surface. I mean, this is at altitude which keeps on gradually increasing from the Earth's surface. So this is the variation of small g with small r. R is the distance of the observation point from the center of the earth. When r is 0, that is at the center of the earth, g is 0. As we move toward the earth's surface, the value of small g keeps on increasing. And at the point on the earth's surface, it is maximum. And still if the height is raised, the value of small g keeps on decreasing. So this is the variation of small g with distance smaller, which is measured from the center of the earth. Clear, students? So this was again a very, very interesting question. Okay, let's move to question number 4. Question number 4 is, at what depth? It's a question in which we will have to make use of the variation of g with the depth. This is the formula to be used. In the case of depth, this is the formula to be used, right? So, what we are supposed to find is, at what depth the value of acceleration due to gravity becomes half its value on the surface of the earth. Okay, this is a relatively simple question based on direct formula. At a depth x, below the earth's surface, the value of acceleration due to gravity is given by g 1 minus x by r or r minus x by r. This we have already derived. Mathematically, we have proved this expression, right? While dealing with numericals, we need to directly apply those formulas. So the value of g becomes half its value. So it's given g dash is equal to g by 2. We are supposed to find out the value of x. Right? So let's solve it. G dash is g by 2. R minus x by r. So g get cancelled. So half is equal to r minus x by r. So cross multiplication we get. So 2x is equal to 2r minus r is equal to r, or x is equal to r by 2. So at a depth which is half the Earth's radius, the value of acceleration due to gravity would be equal to half its value on the Earth's surface. Numerically, the radius of the Earth is 6400 km. So it is 3200 km. So at a depth of 3200 km below the Earth's surface, the value of acceleration due to gravity is 50%, that is half of its value on the surface. Clear? So, we have done question number 4 as well, right? So, this question 4 was directly based on the concept of the variation of small g with the depth. Okay, let's try question number 5. Calculate the force of attraction between the two bodies, each of mass 100 kg and 1 meter apart on the Earth's surface. Now we are aware of universal law of gravitation. between any two material bodies there exists a gravitational force of attraction, the magnitude of which is directly proportional to the product of masses of the two bodies and it obeys inverse square law. Suppose these are the two bodies. One is of 100 kg and the other one is of 1 kg. And the distance between them is 1 meter. We are supposed to find out this force. So what's the formula? G m1 m2 divided by r square. So let's substitute the value. Students, you should be aware of the formula of capital G and small g. Small g is acceleration due to gravity, which is 9.81 meter per second square, right? And capital G is universal constant. Its value everywhere in the universe at any place would be constant. It's 6.67 into 10 raised to minus 11 Newton meter square per square kg. So G, its value is 6.67 into 10 raised to minus 11. M1, one of the mass is 100 kg. The mass of the other object is 1 kg. And the distance with them is 1 meter. So 1 square. So what you get is 6.67 into 10 raised to power 10 raised to 2 and 10 raised to minus 11. When the base is same, the exponents get added up. So minus 11 plus 2 is minus 9. This is in Newton. So this is the force experienced by these two bodies. And students, observe the result. It's a huge value or a negligible value. It is 10 raised to minus 9. So it is a negligible value. So this numerical clearly suggests that there does exist some attractive force between these two material bodies, but it is too small to be measured. It's almost negligible. So that is the reason why I have always stated the gravitational force between two terrestrial objects is negligible, while the gravitational force between two celestial objects or heavenly bodies is much more dominating. Clear, students? So any objects which are on the Earth's surface, right? The gravitational force between two persons, the gravitational force between a car and a jeep, all those forces, their magnitude would be negligible. That is what we have proved over here. But between planets like Earth, Moon, like Earth, Sun, the gravitational force is huge. And it is this gravitational force that enables the Earth to revolve around the Sun, or it enables the Moon to revolve around the Earth. Right? So we are over with question number 5 as well. Now let's concentrate on question number 6. It is also very simple. Based on theoretical facts, we will make use of the mathematical expression of universal law of gravitation. Question 6 is, what happens to the force between two objects if mass of one object is doubled? Now look, students. Force, the master formula between the force existing between two material bodies is given by G m1 m2 by r square. This is the formula. Right? This is the basic formula to be used. Mathematical expression for the universal law of gravitation. Okay, now let's consider the first part. Mass of one of the object is doubled. Now what happens is, let m1 dash is equal to twice m1. Out of these two masses, one of the mass get doubled. So what will happen is new force. It will be equal to G in place of m1, write m1 dash, which is equal to twice m1. Right? The other mass is same, divided by r square. So what do we get? Twice G m1 m2 by r square. So it is equal to twice G m1 m2 by r square is F. So it's pretty evident that if out of the two bodies, mass of one of the bodies is doubled, then the gravitational force between those two bodies will also get doubled. So F dash will also become twice of the original force. Clear, students? Okay. Let's consider the second part. The distance between the objects is doubled and tripled. There are two parts. First we consider when the distance between the objects is doubled. Now look over here. If r dash is equal to twice r, then what will happen is F dash it will be equal to mass remains same, m1, m2. So here it will be, instead of writing r, we will write 2r. So it will be 1 by 4 G m1 m2 by r square. That is 1 by 4 and this is the original force. So students, if the distance is doubled, then the force will become quarter, that is 1 by 4th. If the distance is made 3 times, it will become 1 by 9 times. So similarly, if r dash is equal to 3r, it will be inverse square law. Then f dash will be g m1 m2 divided by, in place of write r, write 3r. So we will get 3r whole square. So it will be equal to 1 by 9 g m1 m2 divided by r square. So it will be equal to 1 by 9 times f. So it's pretty simple. Look, f is inversely proportional to the square of the distance. This we have discussed is known as inverse square law. So students, if r is made twice, then force will become 1 by 4 times. If r is made 3 times, then f will become 1 by 9 times. If r is quadrupled, that is if r is made 4 times, then the force will become 1 by 16 times. If the distance is made 5 times, then the force will become 1 by 25 times. Clear? Similarly, if the distance is increased to 6 times, then the force within those bodies will become 1 by 36 times. It obeys inverse square law. It is inversely proportional to the square of the distance between the two given bodies. Right? Okay, last part. The masses of both the objects are doubled. Okay, third part is masses of both the objects are doubled. Both the bodies. Right? So what to do is m1 will become twice m1, m2 will also become twice. So, third part. Now m1 dash, new mass would be twice m1 and the other mass would be twice m2. So new force, it will be equal to g m1 dash m2 dash divided by r square, isn't it? So substitute the value. G m1 dash is twice m1, m2 dash is twice m2 divided by r square. So that will give us 4 g m1 m2 divided by r square. So what you get is 4 times the original force. So it is but obvious that if masses of both the bodies is made twice, then the gravitational force between those two bodies will become 4 times. Right? So we are over with question number 6 as well. So students, I sincerely hope I am able to make your concepts clear. Right? So you all must be very, very convinced doing such questions. You need to feel confident doing such numericals. Right? And that confidence can be achieved, students, only and only through hard work. So never shy away from working harder and still harder. Right? So with that note, I'll conclude this session. We'll continue in the next lecture then. Till then, do take very good care of yourself. Thank you.